Good evening everyone. I'm Naveen. Today I'm excited to discuss about ImageGPT. These are the table of contents we are going through today. The pivotal role of unsupervised pre-training in the resurgence of deep learning, particularly from the mid 2000 onwards. Initially, techniques like deep belief networks and denazing autodecoders were instrumental in tackling the challenges posed by unlabeled data. They help lay the foundation for subsequent advancements in the field. However, as deep learning progressed, we witnessed remarkable improvements in the activation functions, initialization techniques, and normalization strategies. These advancements reduced the dependencies on pre-training for achieving strong results, leading to the widespread adoption of end-to-end training. Despite these strides, generative modeling, especially for images, remained a formidable challenge. Yet, with continued progress in architecture, design, training objectives, and the availability of robust computational resources, generative pre-training has emerged as a potent competitor to self-supervised methods. Our comprehensive experiments across various datasets and evaluation settings provides compelling evidence of the efficiency of this approach. Not only do they showcase its performance, but they also offer valuable insights in the representation, computation, and scalability. I will be walking you through our approach to image representation. We begin by pre-processing raw images, a crucial step in our pipeline. We resize the images to a lower resolution and reshape them into one-dimensional sequence. This step helps us efficiently process and analyze the images. Next, we have two pre-training objectives to choose from: autoregressive next pixel prediction or masked pixel prediction. These objectives serve as a backbone of our model, guiding it to learn meaningful representations from the input images. Finally, we evaluate the representations learned by these objectives using two main techniques: linear probes and fine tuning. Linear probes allow us to assess the quality of learned representations in the controlled setting, while fine tuning further refines the model performance for specific tasks. Our approach comprises two main stages: pre-training and fine-tuning. During the pre-training stage, we dive into both the autoregressive and BERT objectives. Unlike traditional language tasks, we apply the sequence transformer architecture to predict pixels of language tokens. This allows us to effectively model image data. To assess the quality of representations learned during pre-training, we employ two main strategies. First, we fine-tune the pre-trained model of image classification tasks. This allows us to evaluate how well the learned representations generalize to downstream tasks. Additionally, we use the pre-trained models as a feature extractor, extracting features from images and training a linear classifier on top. This provides another perspective on the quality of learned representations. Pre-training serves multiple purposes in our approach. It acts as both favorable initialization for subsequent tasks and a form of regularization when combined with early stopping techniques. This ensures that the model learns robust, generalized representations during pre-training. We dive into the realm of image classification methodology. Traditionally, supervised pre-training has been the dominant approach. However, it's crucial to acknowledge the challenges posed by curating large labeled datasets. Not only is it expensive, but it's also incredibly time consuming. To tackle this issue, we propose a different approach: learning general purpose representations from unlabeled images and then fine tuning them for clarification tasks. This allows us to leverage the vast amount of unlabeled data available. Specifically, we are utilizing ImageNet as a proxy for a large unlabeled corpus. For our downstream tasks, we are relying on classic labeled datasets such as Cipher10, Cipher100, and STL10. For our training and validation, we are using the ImageNet ILS VRC 2012 dataset. Additionally, we are conducting experiments on Cipher10, Cipher100, and STL10 datasets to further validate our approach. To optimize our model, we have adopted a customized color palette. This reduces context length while still maintaining the color fidelity, enhancing the efficiency of our model. In terms of technical details, we are carefully considering batch sizes, iterations, and optimization strategies for both pre-training and fine-tuning stages. In this experimentation, we have subsections, which covers the following: representation in a generative model without latent variables. Better generative models learn better representation. Linear probes on Cipher and STL10. Linear probes on ImageNet. Full fine-tuning. BERT. Low data Cipher10 classification. Coming to the fascinating world of representation quality in generative models, as we explore this slide, we uncover a crucial aspect. Representation quality depends on the layer, which we extract features. Unlike supervised models, where representations tend to improve with depth, our findings reveal a unique pattern. In our experiments with IGPT-L on Cipher10, Cipher100, and STL10 datasets, we observed that the best representations for these generative models actually lie in the middle of the network. This unimodal dependencies on depth is vividly illustrated through linear probes, showcasing a distinct shift from conventional wisdom. This insight challenges traditional notions and opens new avenues for understanding the inner workings of generative models. As we continue our exploration, we will uncover further enhances that redefine our understanding of representation learning. Here we have a plot illustrating the relationship between representation quality and validation generative loss. Each line is on the plot represents a different model tracked throughout generative pre-training. The dotted markers indicate checkpoints at specific steps: 65K, 131K, 262K, 524K, and 1000K. What's interesting to note in the positive slope of the lines, indicating a clear link between improved generative performance and better representation quality. This suggests as the model improve in their ability to generate data, they also enhance their capability to represent information effectively. Furthermore, we have observed larger models tend to produce better representations, both towards the end of training and at the same level of validation loss. This confirms the importance of scale in our approach. It's worth mentioning that the IGPT Excel model is not shown in this plot, since it was trained on a different datasets, but its absence doesn't detract from the overall trend we are seeing here. We get into the evaluation of learned representations of Cipher100 and STL10 datasets, aiming to understand how well our model generalizes across various datasets. These findings reveal an impressive achievement on the state-of-the-art performance across different pre-training approaches. This indicates the robustness and versatility of our model. What particularly exciting is the superior performance of our linear classifier fitted to representations of IGPTL compared to the end-to-end supervised training model of a wide ResNet baseline on all three datasets. Our model consistently outshines in the performance, even on datasets like STL10, which present varying input resolutions. Our model demonstrates remarkable performance by employing downsampling before linear probing. We ensure that our model adapts effectively to diverse input resolutions. Furthermore, we have explored the efficiency of fine-tuning as a strategy to adapt models trained at the high input resolutions to low input resolutions. This underscores the adaptability and flexibility of our model in addressing different input scenarios. Let's get into the comparison of linear probe accuracies between our model and state-of-the-art self-supervised models. As you can see from the table, we meticulously compared the performance of our models with various contrastive methods. The blank input resolution, which signifies a model operating at the standard ImageNet resolution. Our findings reveal that our model consistently achieved comparable performance to the best performance configurations to each contrastive method. This underscores the efficiency of our approach is achieving competitive results with the realm of self-supervised learning. In this slide, we are comparing the fine-tuning performance of our models with the state-of-the-art models that utilize supervised ImageNet transfer. Additionally, we have included AutoAugment, which is recorded as the best performing model trained end-to-end on Cipher. As you can see in the table, we have listed the models along with the respective accuracies on Cipher10, Cipher100 datasets as fine-tuning. Our model IGPTL achieves an accuracy of 99% on Cipher10 and 88.5% on Cipher100 after fine-tuning, showcasing its impressive performance. These results are comparable and in some cases even surpass those achieved by other state-of-art models. For instance, on Cipher10, our model's performance matches that of GPAP, which known for pre-training using ImageNet Enable. Similarly, on Cipher10, our model outperforms CLR, a prominent pre-training approach, and even auto-augment the leading model trained end-to-end on Cypher. These findings underscore the effectiveness of our approach and highlight the competitive edge of our model when it comes to fine-tuning performance of Cypher datasets. Let's take a closer look at the comparison of autoregressive pre-training and BERT pre-training using IGPT-L at an input resolution of 322 by 3. As you can see in the image, the blue bars represent the linear probe accuracy, while the orange bars represent the fine-tune accuracy. The bold colors indicate the performance boost from the assembling BERT masks. What's interesting here is that autoregressive models initially produce much better features than BERT models as pre-training, as indicated by the higher blue bars. However, after fine-tuning, BERT models manage to catch up as shown by the comparable orange bars. This highlights the dynamic nature of pre-training methods and the importance of fine-tuning in maximizing model performance. It also emphasizes the potential BRT pre-training in enhancing features representation, especially in downstream tasks. Now let's get into the performance of IGPT on low data cipher 10 classification. By leveraging a large number of unlabeled images from ImageNet, IGPT-L demonstrates a superior performance compared to established methods such as mean teacher and mix match. However, it's important to note that while our approach surpasses these methods, it still falls short of the state-of-art techniques as reported by XIE ETL and SON ETL. What sets our approach apart is its simplicity. Unlike specially designed semi-supervised approaches, we adopt a straightforward strategy. We simply fit a logistic regression classifier on the features extracted by IGPT-L without resorting to any data augmentation and fine-tuning. This minimalist approach yields competitive results, showcasing the effectiveness of leveraging the pre-trained features of IGPT-L. It's worth mentioning that other results reported from Mixmatch, another recent approach, further validates the efficiency of our approach. These are the related works. Generative models like GANs and VAEs have been extensively studied for representation learning. However, most generative model approaches have not been competitive with supervised and self-supervised methods in the image domain, except for Big BGAN. Many self-supervised approaches focus on designing auxiliary objectives to learn useful representations without directly modeling the input data. Contrast to approaches such as constructive predictive coding and selfie have shown significant progress in the self-supervised learning. Previous investigations by Collins, Kolenskov have highlighted the benefits of the scale and non-monotonic performance of representations with the depth in certain architectures. Pixel by pixel cipher 10 task introduced by KTL benchmark the performance of a 1D sequence transformer on a competitive image classification dataset. Autoregressive models applied to image were first introduced by Uria et al. In 2013 and popularized by Old et al. In 2000. Generative image modeling continues to show great promise on the realm of unsupervised learning, particularly in the realm of learning high-quality image representations. By simply predicting pixels, we have managed to achieve state-of-the-art representations, even on low-resolution datasets. Moreover, this approach remains competitive even in high-resolution settings such as ImageNet. However, there are certain areas where improvement is needed. One major hurdle is the necessity of large models, which can be both resource-intensive and computationally expensive. Additionally, the dense self-attention mechanism, while powerful, also adds to the computational overhead. As we move forward, further research endeavors could focus on developing more efficient self-attention mechanisms. This might involve exploring alternatives like local 2D relative attention, implementing sparse attention patterns, or even leveraging locality sensitive hashing techniques. Additionally, adopting a multi-scale model approach could offer further insights into enhancing efficiency while maintaining performance. Furthermore, it's crucial to not limit ourselves to a single approach. While the results we have obtained with the generative models like IGPT are impressive, there is still much more to explore. It would be worthwhile to dive deeper into the representation learning capabilities of other generative model families, such as flow-based models and variational autoencoders. Previous studies have shown competitive results in these areas. And in conclusion, while generative image modeling has already made significant strides, there is still plenty of room for growth and innovation. By addressing challenges like model size and computational complexity, and by exploring a broader range of generative model architecture, we can continue to advance the fields and unlock new possibilities in the supervised learning and image representation. Thank you.